Hello everyone, this is Dr. Webb and welcome to this abstract algebra video where we are going to be talking about splitting fields. So, what exactly do we mean by splitting? Well, when we're talking about splitting, we're talking about take a polynomial factoring. So if a polynomial factors completely, that means that it splits. So our exact definition of splits is if we have some polynomial f of x, that's polynomials are in K, and K is a subfield of L, well, we're going to say that f of x splits in L if, when we look at f of x in L adjoin x in the polynomials over L, f of x factors into a product of linear polynomials, right? And so these linear polynomials, the constant out in front, you can think about this as sort of the coefficient of x to the n, and then all of the roots here, alpha 1 through alpha n, are all inside of L. So this f of x has factored completely, or in other words, has split in L. So some examples, if you look at, say, 2 times x squared minus 10x plus 12, well, this actually factors in the rational numbers. It turns into 2 times x minus 2 times x minus 3, and so we would say that it splits in Q, splits in the rationals. If we look at x cubed minus 2, well, this splits in Q adjoin the cube root of 2 and omega, where omega is the cube root of unity, because you can factor it into x minus the cube root of 2 times x minus omega times the cube root of 2 times x minus omega squared times the cube root of 2. So it has factored completely. It has split. So note that f of x is going to split in L if and only if every root of f of x is in L. Right? This is a necessary and sufficient condition for f of x to split. If all the roots are in there, then it's going to factor completely into linear polynomials, so it will split. If f of x splits in L, and L is a subfield of f, well, then that means that f also contains every root of f of x, so f of x is going to split in f as well, right? So once it splits in L, then it's going to split in every other field that contains L. So this then leads to the notion of what the splitting field for an f of x is. And since whenever you have it splitting inside of a field, it's going to split in fields bigger than that, then the question of splitting field really boils down to, well, then what is the smallest field that it splits in? And so that smallest field is what we're going to call the splitting field. So the precise definition of it is if we have that f of x is a polynomial with coefficients in k, we'll let L be some field over k, we will say that sigma is the splitting field of f of x over L if f of x splits completely in sigma, and for any other field f that contains L that f of x splits in, then sigma must be a subfield of f. Okay, so any other field that f of x splits in that contains L must also contain the splitting field sigma. So this is where we get the notion that sigma is the smallest field that contains L that f of x splits in. And so it's important to note in this definition that even though the coefficients for f of x come from k, we're really able to define this for any field L that contains k. Okay, and so L and k don't have to be the same thing. L just has to be some field where it makes sense to talk about f of x as a polynomial with coefficients over it. Okay, so some examples of this. If we look at the polynomial x squared plus 1 over q, its splitting field is q adjoin I, because x squared plus 1, this factors into x plus I times x minus I in q adjoin I. And that's the smallest field in which this splits. If we want to look at x squared plus x plus 1 over q, well, then its splitting field is q adjoin omega. Omega is one of the roots, and omega squared is the other root. Again, this is where omega is a cube root of unity. Now, if we change the base field for x squared plus x plus 1 to q adjoin the cube root of 2, then the splitting field for that over q adjoin the cube root of 2 is then going to be q adjoin the cube root of 2 and omega. Right? This polynomial x squared plus x plus 1 doesn't split in q adjoin the cube root of 2, but it does split when you would tack omega into that. So let's talk about some quick facts that are easy to see about splitting fields from this definition. So the first is the splitting field for f of x over L has to be L adjoining all the roots of f of x. Right? So if you adjoin all the roots of f of x to L, then f is going to split in it. And so the splitting field definitely has to be inside of here, but if it doesn't have all the roots, then it can't possibly split. So this has to be the smallest field. This L adjoining all the roots has to be the smallest field because it needs all the roots for f of x to split. And if it has all the roots, then it's going to split. And then if sigma is the splitting field, big sigma is the splitting field for f of x over L1, and you have some other field L2, which is in between L1 and sigma, then sigma is also going to be the splitting field for f of x over L2. And this is just coming from the fact that from the first bullet, sigma is going to equal L1 adjoining all of these roots. The splitting field for L2 is going to be L2 adjoining all these roots. But since L2 is inside of L1 joining all the roots, this was a problem in our homework, that means that these two are going to be equal. That if L2 is inside L1 adjoin alpha 1 through alpha n, then if you just adjoin alpha 1 through alpha n onto L2, that's going to give you back this L1 adjoin alpha 1 through alpha n. Okay, so how big can these splitting fields be? Okay, so let's let f of x be a polynomial over k of x whose degree is n, and it's greater than or equal to 1, so this is f of x is not some constant, it is a non-trivial polynomial. And let's let L be the splitting field for f of x over k. Then the dimension of L over k, the degree of L over k, has to be less than or equal to n factorial, where this n is the degree of f of x. So whatever the degree of f of x is, the degree of the splitting field has to be less than or equal to n factorial. So in this, it actually can equal n factorial. In fact, it equals n factorial quite often, but that's going way off into another direction. But one quick example where it equals n factorial is if we look at a polynomial we've looked at quite often, which is x cubed minus 2 over the rationals. And so its splitting field is if you toss in the roots, cube root of 2, omega times the cube root of 2, and omega squared times the cube root of 2. Well, this is the same as the extension q adjoin the cube root of 2 and omega. And we've looked at this extension quite a bit. We know that its degree is 6, and 6 is equal to 3 factorial. And so 3 factorial here corresponds to the degree of the polynomial. It's a cubic. So this is a case where it actually is n factorial, where n is the degree of the polynomial. Okay, so we're going to prove this by induction. And the base case is just n equals 1. So if n equals 1, then our polynomial is just linear. And if it's linear, then the root is already in the base field. So a linear polynomial is going to look like c times x minus alpha, where alpha is already in k. So k is already the splitting field of f of x over k. And the degree of k over itself is equal to 1. Right? And 1 is equal to 1 factorial. So that gets us the base case. Now for the induction step. So what we're going to assume for the induction step is that for any field k prime and any polynomial h of x with coefficients in k prime whose degree is n minus 1, then the splitting field L prime for that polynomial over k prime has degree less than or equal to n minus 1 factorial over k prime. Okay, so that's for n minus 1, we get the degree to be n minus 1 factorial. So let's take our function, let's take our polynomial f of x over k that has degree n. And we're going to let L be the splitting field for f of x over k. And then we're going to let alpha be any root of f of x. Well then, if we look at k adjoin alpha, we can pull out this factor x minus alpha, because alpha is a root of it. Okay, and then, so that means that we can rewrite f of x as x minus alpha times some g of x, where now since f of x has degree n and we factored out a linear factor, our new g of x is going to be degree n minus 1, and it's going to be a polynomial over k adjoin alpha. And if it's a polynomial over k adjoin alpha, since f of x splits completely in L, and g of x is a factor of f of x, then g of x also has to split completely in L. And it can't split anywhere beforehand, because if it splits anywhere less than that, then that means that L wasn't really the splitting field for f of x. So L also has to be the splitting field for this g of x, but now it's over k adjoin alpha. So to finish this off, we're going to apply the Tower law. And so what we want to get our hands on is the degree of L over k. And by the Tower law, we're using the fact that k adjoin alpha now is sitting in between the two, so we can plug that in. So the degree of L over k is going to equal to the degree of L over k adjoin alpha times the degree of k adjoin alpha over k. Okay, now we're going to look at each of these terms on the right. And let's first look at this k adjoin alpha over k. Well, so how big could this be? Well, this is going to be the degree of whatever the minimal polynomial for alpha is. And so if f was the minimal polynomial for alpha, then that means that this is degree n. If f is not the minimal polynomial for alpha, well, but alpha is a root of f, and so that must mean that the minimal polynomial for alpha divides f. So then min poly of alpha divides f of x in k. And so that means that the degree of the minimal polynomial for alpha in k has to be no bigger than the degree of f, which is n. And so since this is equal to the degree of the minimal polynomial, we can say the degree of this extension right here, this can't be any bigger than n. Okay, and so we can plug that in. So now replacing the degree of this extension by n, so that tells us that now the degree of L over k has to be less than or equal to n times our degree of L over k adjoin alpha. And so now for this part, we're going to apply our induction hypothesis. And so this is going to be, since L is the splitting field for g of x over k adjoin alpha, and g of x has degree n minus 1, that means that this has to be less than or equal to n minus 1 factorial. And so we end up with that the degree of L over k has to be less than or equal to n times n minus 1 factorial, and this right here is n factorial, and that completes the proof. Okay. So, why are we talking about splitting fields? How is this going to fit into what we're doing? So the big goal that we're working on right now, that we're working towards, and we're not going to be able to finish it in this video. It's going to take 1 or 2 videos more. But the big idea is that what we're going to end up proving is that a finite extension L over K is Galois. So remember, Galois, this was a concept we've been talking about the last couple of videos, and that's when the degree of the extension is equal to the size of the Galois group. So the number of elements of the Galois group is equal to the degree of the extension. This is going to happen if and only if L is the splitting field for some polynomial over K. So this is how splitting fields are going to work in. This is going to give us a necessary and sufficient condition for extensions to be Galois. So leading towards that, we're going to need some technical results. And so this is the big technical theorem for this video. And it's going to tell us when we can get maps from one splitting field to another, essentially. Okay, and so theorem is we're going to have 2 fields, K and K prime, that are isomorphic, and phi is the isomorphism between them. We're going to take some polynomial f of x with coefficients in K, and we're going to let sigma be its splitting field over K. And then on the K prime side, we're going to be looking at what f maps to, and so that's phi of f of x. And then we're going to take any field L prime that phi of f of x splits in. Then what has to happen is there then has to be some field homomorphism, we're going to call it psi, that maps from sigma, this is the splitting field of f of x, into L prime. So this is some field that phi of f of x splits in. And the condition on this psi is that if we restrict psi to K, and so what that means is we just think about what happens when we plug in things from K into psi, then this map is the same thing as what is phi, right? So this psi sub K, what this really means is we're looking at what happens to psi if we change the domain to K, and in that case, the homomorphism just turns into our isomorphism phi. So let's draw a quick diagram to exactly what's going on here. So we've got our K and our K prime, and we have this isomorphism going between them. So these are 2 isomorphic fields. And then over K, we have this splitting field sigma for f, and over K prime, we have this field that phi of f of x splits in. We're going to call that L prime. Okay, so this homomorphism from K to K prime, this is our phi, and phi is going to jump up into a homomorphism that really is going to complete this diagram, and that's going to be psi. And so that's really what's going on here. Okay, so our strategy to prove this is we're going to rely heavily on a theorem that we proved back a couple videos ago in video 6. And what that theorem was, and this should be, I made a typo here, this should be K prime. I changed the notation in it to match what we're doing here. And so the theorem from video 6 that we're going to be using is that starts off again, we have K and K prime that are isomorphic to each other. And if we have a irreducible polynomial g of x over K, and if alpha is a root of g of x and beta is a root of phi of g of x, then there's an isomorphism from K adjoint alpha to K prime adjoint beta. Okay, and so we're going to use this over and over again. But note that our restriction here on our g of x is that it has to be irreducible. This is not the restriction that we have before for the big theorem that we're trying to prove right now. It's true for any f of x. This theorem only applies to irreducible polynomials. So we're going to have to keep on talking about irreducible factors. So let's get rolling. So we have our f of x. We're going to take a g1 of x to be an irreducible factor of f of x over k. And then we just take alpha 1 to be any root of g1 of x. So since g1 of x is a factor of f of x, its roots have to live in sigma. So alpha 1 is something in sigma that's the root of g1 of x. Okay. Well, then if we then throw g1 into phi, then phi of g1 has to be an irreducible factor of phi of f of x. And this comes from the fact that k adjoint x is going to be isomorphic to k prime adjoint x. And so then we take some b1 to be any root of phi of g1. Okay, and b1, since phi of f is going to split in L prime, then beta 1 has to be something in L prime. So now we can apply this theorem from video 6. We get an isomorphism. We're going to call it psi 1, and it's going to go from k adjoint alpha 1 to k prime adjoint beta 1. And so in this isomorphism, psi 1 is going to send alpha 1 to beta 1, and it's going to just send stuff from k to k prime the same as our isomorphism phi. And so this is how the isomorphism was constructed when we proved the theorem in video 6. Okay. And so now we're going to do this again. But now we're going to be starting at k adjoint alpha 1. And so we're going to let g2 now be an irreducible factor of f of x once we've now divided out x minus alpha 1. So g2 is an irreducible factor of f of x divided by x minus alpha 1. And now we take alpha 2 to be a root of this. So if alpha 2 is a root of this means that it still is a root of f of x. And so same as before, now we can look at tossing g2 now into psi 1. And we can take beta sub 2 to be any root of that. And then apply this theorem again. So psi 2 is going to be an isomorphism now from k adjoint alpha 1, comma alpha 2 to k adjoint beta 1, beta 2, where psi of 2 now is sending alpha 2 to beta 2. And if we look back at just k adjoint alpha 1, so this is what we have before we added in alpha 2, this isomorphism is going to be the same as psi 1. So psi 2 is just building off of psi 1. And psi 1 was building off of phi. So we have this kind of chain. Now as we're going from, think about how we're doing this. We started off k going to k prime. That's our phi. And then we went up to k adjoint alpha 1. And this is isomorphic to k prime adjoint beta 1. And we have our psi 1. Psi 1 is our isomorphism there. And then now in this step we've now gone up one more step to k adjoint alpha 1 and alpha 2. And it's going to be isomorphic to k adjoint beta 1 and beta 2. And then our new map is psi 2. And so then the idea with these maps, psi 2, psi 1, and phi is whenever you go down a level, psi 1 is going to match, psi 2 is going to match psi 1. And then you go down a level again, then it's going to match phi. So if we take any element in our base field k, well, if it's in k, k is inside k adjoint alpha, so alpha is also in k adjoint alpha 1. And so then that means that psi 2 applied to y is going to equal psi 1 applied to y, because y is in k adjoint alpha 1. But then in psi 1 of y, well, psi 1 restricted to k is equal to phi, and y is in k. And so psi 1 of y is going to equal phi of y. And if this is true for all y in k, then that means that if we restrict psi 2 to k, we're going to get the same map as phi. It's equal to phi. So psi 2 restricted to k is equal to phi. So we do this process again. Now we take a g3 of x, which is an irreducible factor of now f of x with both x minus alpha 1 and x minus alpha 2 divided out. And we just keep on going, etc., etc., etc. We keep on doing this process until we get our f of x to splitting completely. And so let's say it takes n times. And so we end up with this map psi sub n that goes from k adjoint alpha 1 through alpha n, and it's isomorphic to, it sends everything to k prime adjoint beta 1 through beta n. So let's, again, we've got k going to k prime via phi, and we had k adjoint alpha 1 going to k prime adjoint beta 1. And this is our psi 1. And then we just keep repeating this process until we got up to alpha 1 through alpha n is isomorphic to k prime adjoint beta 1 through beta n. This gives us our psi n. And so again, we've done this for joining every new alpha I is going to give us some new beta I, give us a new map, psi I. And these maps are all isomorphisms between the two. And if we ever go down a level, psi n is going to match psi sub n minus 1 for k adjoint alpha 1 through alpha n minus 1. And we just keep that going down all the way down. And so at this point, f of x has split completely, and it didn't split completely anywhere beforehand, so this k adjoint alpha 1 through alpha n has to be our sigma, right? Because this is the first place that f of x has split completely. So now we have an isomorphism between sigma and k prime adjoint beta 1 through beta n. Now, we wanted our map psi to go from sigma to L prime, and so here it's basically done. And so we'd say this induces our map from psi going from sigma to L prime. And so why are we basically done? And so technically what psi is going to be is it's going to be this psi sub n right here composed with another map iota, where iota is just what's called the inclusion map from k prime adjoint beta 1 through beta n into L prime. So it's just a homomorphism since k prime adjoint beta 1 through beta n, since this is a subfield of L prime, there is a natural inclusion homomorphism that just sends from k prime adjoint beta 1 through beta n into L prime, that just sends everything to itself in L prime. And so that's what our psi is going to be. So a near immediate corollary to this is that if our L prime on the other side was actually the splitting field for phi of x, and so instead of calling it L prime, we're going to call it sigma prime, then this map actually is an isomorphism. Okay, and so this is often what's called the, let's pick a better color, isomorphism extension theorem. Okay, and so what it says, if we have the same setup as before, K and K prime are fields, and phi is an isomorphism between them, and you take some polynomial f of x, which is non-zero over k, and you let sigma be the splitting field for f of x, then sigma over k is going to be isomorphic to sigma prime over k prime, where sigma prime is the splitting field of the image of f, so phi of f of x over k prime. Okay, and so the difference here is that sigma prime is not just any field that phi of f splits in, it is the splitting field for phi of f. Then we get an isomorphism. And so by the theorem that we just proven, since phi of f is going to split in its splitting field, we get the homomorphism psi. That should be psi there, not phi. That should be psi there, going from sigma to sigma prime, with psi restricted to k equaling phi. But then, since in our construction of this, phi of x is going to split in the image of this map psi, and again, this should be psi. Well, since it splits in the image of psi, then the image of psi must be the splitting field, because it's going to be inside of sigma prime, but sigma prime is the smallest field that phi of x splits in. So you must have the image of the map equaling this. And so for a field homomorphism, if the image matches the range, then this must be an isomorphism. Right, so this is an onto map, and all field isomorphisms are one-to-one. So it's one-to-one, and onto gives us an isomorphism. Okay, so let's take a deep breath. What is a good use for this? Let's think about what this means tangibly. And so this is a very important consequence of this theorem, and corollary together. And this is a good way to think about what these are saying. It's a good application for this, right? And so let's start with f of x being an irreducible polynomial over k. And let's let alpha 1 and alpha 2 be two roots of f of x. And let's let sigma be their splitting field of f of x over k, right? And so really for this part right here, we're using k prime is going to equal k. Or really what we're going to be doing is going to be using an isomorphism between k adjoint alpha 1 and k adjoint alpha 2. You can think about it in either of these two ways. Okay, so by their construction in the proof, we have an isomorphism, let's call it sigma 1, from k adjoint alpha 1 to k adjoint alpha 2, where this sigma 1 is going to send alpha 1 to alpha 2. And sigma 1 is going to be the identity on k. Okay. So now by our isomorphism extension theorem, this sigma 1 can now be extended to an isomorphism to the splitting field, sigma. And it does the same thing that it did on k adjoint alpha 1. So sigma is going to send alpha 1 to, not sigma of alpha 1. Sorry, that should just be alpha 2. And sigma fixes k. So what do we have? Let's make sure that says alpha 2. So in other words, we have constructed a k automorphism. It's an automorphism because it's an isomorphism from sigma to itself. It's a k automorphism because it's fixing k. And this k automorphism of sigma is sending alpha 1 to alpha 2. Well, if this is a k automorphism of sigma, of big sigma, this means that it is in the Galois group of big sigma over k. Okay. So putting this all together, we have this new corollary that says that if f of x is an irreducible polynomial over k, and we have that alpha 1 and alpha 2 are two roots over f of x, and sigma is the splitting field for f of x over k, then there must be something in the Galois group. There must be some k automorphism of sigma such that sigma of alpha 1 is equal to, and again, that should just be alpha 2. Okay, so there is, if alpha 1 and alpha 2 are roots of the same irreducible polynomial, then when you go to the splitting field, sigma, there's going to be an element of the Galois group that sends alpha 1 to alpha 2. And so this is the really big important stuff. So if you have two elements, they're conjugates of each other, they are roots of the same irreducible polynomial, then when you go to the splitting field for their irreducible polynomial, there's in some element of the Galois group that's going to send one to the other. So that is all for this video. I will see you again soon.